Okay. Gosh, I'm tempted to not record this at all for the seniors that are not here. It's present, but juniors, the juniors, it's not their fault, so I'm going to record. All right, so here we go. Find the area under. Now this, we're going to start with what we've done before. We're going to then go into what I'm adding today, and then we're going to practice the whole process all the way through, and it's going to go great. So yesterday and the last couple of days we talked about how to do area under the curve without so much of the base height, and we're in a summation notation approach, right? So I hope that you've gathered the first thing we typically do is write a summation of bases times height, where base goes to how wide each subregion is, and height comes from the function, but the function at lots of different x's depending on where you start and how many rectangles over. Yeah? So for this problem, I might say my first step is the area is the accumulation or the sum of many bases times height, and I would then start by finding what delta x is. For this problem, delta x comes from dividing a region that's 3 wide into how many chunks? N chunks. If they don't say use 7 rectangles, then it's just a predetermined, or unknown number of rectangles. If you're not clear where that 3 over n is coming from, that's not. Okay? The height, remember, comes from, I just told you we're not going to use a picture, but just to make sure we're clear, the height comes from starting at 1 and going over 1 delta x and drawing the height, or 2 delta x and drawing the height. So the height is always f starting at 1 and going some number of 3 n's over, whether it be 1 3 over n over, or 2 3 over n's over, or I 3 over n's over. Now when I'm using right-hand rectangles, I'm going to start by going exactly 1 3 over n over, so I start by going at 1 and going 1 delta over, and it'll end by starting at 1 and going n, or whatever the number of rectangles you want me to draw. You follow? Okay? After that, we start to get function specific. In this case, the function is 3x squared. So rather than write this as f of this, I'm going to write this as 3 over n times 3 blank squared, because that's what the function is. And in that blank goes all these different x's I'm trying to put in. 1 plus 3 over n I times. Wait? All right. Then the part where we're gradually adding in is breaking this up into lots of little pieces, and today you'll see why we would want to do that. I could, maybe in 2 steps, clean this up pretty well. I could put 3 over n out front and 3 times, and when I square that, I don't know, maybe I should do this in 2 steps. I don't know. I don't want to skip steps and get confused, so I'm going to be careful. Maybe do this in 2 steps. 3 over n. So when I go to expand this out, I have 3 times first 1 plus 3 over ni plus 3 over ni, so that's a total of 6 over ni's plus 9 over n squared I squared. All right. Now then, the many summations. The first term I'd have is a constant in there. Altogether, I'd have a 3, and I'd have a 3n out front. So I could write 3n times the sum of a bunch of 3's. Then I could write 3n times all the I kind of terms. Now, I took that 3 over n out, and I would also have 18 over n that I could take out. Are you with me? And what's left then inside the sum is just an I. okay? Last but not least, the squared terms. I would have a 3 over n out front, and I could also take that n term, but remember that's times a 3, so altogether 3 times 9 over n squared, that would mean a 27 over n squared outside of the sum of a bunch of I squareds. And that's where we stop. You with me? Now we go on. So then the question of the day is, all right, great. What now? Yes?
Can you take out the 3 n's earlier on, like?
Sure. Probably better. Yeah, that's a good idea. Yes, absolutely. Okay. You could take the 3 over n out front earlier. You could probably do this algebra in a little quicker ways. I might not have done it as efficiently. All right, now, if I take this, I just import, I don't know if you need to rewrite it, but. All right, now, if this idea represents the area under the curve using some number of rectangles, okay? So it's an area estimation function. And if I wanted to use one rectangle to estimate the curve, then I could put n equals 1 in and get some kind of estimate. If I want to use 2 rectangles, I could put n equals 2 and get some kind of estimate. But the idea of perfect area is to take the limit as the number of rectangles goes to infinity. The more rectangles you take, the less error you get. I don't know if I think that's clear at this point, but just so it's abundantly clear, 1 rectangle would stink because I've got all that error. 2 rectangles would be better because by going to 2 rectangles, all this, what that was error over there, has been removed, and now I get less error. Yeah? To the extreme, you get less and less and less green areas. All right, so then, we want to take the limit as n goes to infinity of our function, this. But, you know, that's pretty dicey. You know, limits are, we're pretty good at limits, don't get it wrong, but the limit of that big summation thing, that's pretty gross. Instead then, we want to dump all this summation stuff and make it a little more like a limit problem we're used to. Now these summations, these sigma notations can be replaced by a little bit of background math that's hundreds of years old. Okay, for example, this guy here, this 3, that summation, doesn't it just mean add a bunch of 3's? How many 3's? And it 3's, okay? This would be when I equals 1, you put down a 3. When I equals 2, you put down a 3. When I equals 3, you put down a 3, and you continue to do that until you got to wherever they told you to stop. Well, then you'd have a bunch of 3's. Well, how do you do repeated 3's? Or 3, how many times? 3 n times. How do you do 3 added to itself n times? 3n, that's multiplication. Yeah, I mean, that's 3 multiple times. That is nothing but 3n. That summation, that big bunch of 3's, it's just 3 n times. Now that one's pretty straightforward. The other one's a little less so. This guy I, this is actually one of the best stories in all of mathematics. Would you like to hear a story? Okay. So first of all, this means what? If you were to say, interpret this to your little brother who's in 3rd grade, this is just the same as 1 plus 2 plus 3, and continuing to add numbers until you get to the end point. And now, what is the sum of 1 plus 2 plus 3 plus whatever until n? Well, let's go to the classic story. Oh, my favorite story time. Now, it goes this way. Correct? Stop me if you've heard this. Have you heard this story? I haven't even started. How would you know? So, the story goes like this. In Germany, about closer to 400 years ago, this teacher of, they're a mixture of kids and ability, they're grouped by ability, from about 5th grade, or 5-year-olds to about 8-year-olds. And this teacher of this class in Germany says, you know what, I'm just not feeling it today, so wanting to buy himself some time to read his paper, he says, all right, kids, I want you to add the numbers from 1 to 100. Go. And he figures, all right, I have some time to drink my coffee and read my paper. He puts his feet up, and not 5 seconds later, some 5-year-old little, the youngest kid in the class, the snot-nosed little kid, brings his slate up. They did their work on little blackboards. Brings his slate up with just the answer. Boom. There you go. And the teacher goes, just do the problem, okay? I want to read. He goes, no, I did the problem. That's it. And the teacher, being a knucklehead, said, okay, I'll do this thing, 1 plus 6 plus blah, blah. And he did all the addition in order like a moron. And he found, 20 minutes later, that, yeah, the answer was correct. The answer is 5,050. How did the kid do that? 5-year-old. Let me help you a little. I'll draw this one. This number. Does that help you? Come on, a 5-year-old can do it. A 5-year-old did it. You know, I have to what? 100. Not 100. Well, you could group them to 100, but I was thinking you'd add them to. Okay, each rainbow adds to another one. How many rainbows? 50. There are 50 pairs of numbers from 0 to 10, yeah? So what's 50 times 101? 5,050. Now, that kid figured that out. That actually was named before. He figured out himself. That kid, 5-year-olds figured that out. Can you believe that? You can't believe that. Obviously not his own dog. You can't even speak. That kid is actually the greatest mathematician of all time. His name is Gauss. And this guy was so amazing that by the time he was 14 or something like that, he had a doctorate. By the time he was 19, he had discovered so many things, basically your age, discovered so many things that he was tired of taking credit for all these amazing ideas. He just would send it to his friends and say, hey, you took credit for that. The guy's the greatest of all time, Gauss. This here curve, which you call the normal distribution, that's the Gaussian distribution. So that's one of the million things he's when he was about your age, he was doing that. Coming up with it. Okay? Now, that said, the formula then, you would say doesn't this correspond to the final number? When you looked at that 101, wasn't that the terminating number plus 1? Yeah? And then what did we do with that sum of each rainbow? Each rainbow was 101, and we multiplied it by 50. And where did 50 come from? Half of the n. That is the formula for, what kind of sequence is this? You learned this last year. That's what makes me so sad. This is an arithmetic sequence. It is an arithmetic sequence where you add to get the next term each time. In this case, you're only adding 1 each time. That's the sum of an arithmetic sequence. All right. You'll also need the formula for a square. Now, to find the other ones, squares and cubes, that actually helps to know calculus because you'll see the growth rate is what it becomes all about. And this is a fun exercise, but for the purposes of time and not going down a rabbit hole on some smaller idea, you could find the sum of a bunch of squares, 1 squared plus 2 squared plus 3 squared, by virtue of that formula. All right. Now, if each of these is equivalent to those summations, then I can use each of those in place of them in my formula. So 3 over n, and in place of that guy, I'm going to use 3n. I don't know the purpose behind my colors. Okay? This 54 over n squared, I'm I'm going to multiply that by the replacement for the sum of a bunch of constants, or the arithmetic sequence 1 plus 2 plus 3 plus etc. by n plus 1 times n over 2. And then this last 81 over n cubed, instead of being multiplied by its summation, I'm going to multiply it by this formula for a sum of a bunch of squares. Adding a bunch of squares can be done by using this formula. Now, you might be asking, do I need to memorize those formulas? The answer is no. I'm not real big on multiplication, and it's not worth memorizing. You would not need to know it for the AP test. I will give you those formulas if you need. All right? Now, that's great. That's a new formula for area based on any number of rectangles. And by writing it this way, we will now be able to take an infinite limit. As the number of rectangles goes to infinity, now because it's going to infinity, that means it's an issue of end behavior. This first guy, this first term, we could easily just hack away the ends, and as n goes to infinity, that's just always going to be 9, all right? Now, this one. This goes to your kind of skill as a n behavior specialist, but power-wise, isn't it n squared over n squared in terms of dominant powers, yes? If it's n squared over n squared, don't those n squareds pretty much knock each other out? And it's all about the constants. And so the constants are 54 over 2. Okay? The last one, in terms of n powers, it's n times n times n, or n cubed, over n cubed. Those powers knock each other out. And then it's just about the constants. So that's something like 81 times 2 over 6. Cleaned up then, 9 plus 27 plus 27. And so the perfect area under the curve, the exact area under the curve, is 54 plus 9 or 62. Now if I put this in my calculator, my summation formula, and put in 100 rectangles and 1,000 rectangles and 1,000,000 rectangles, you would gradually see it closer and closer to 63, 63.1, 63.0001. But that theoretically is exact. Okay? Oops, I kind of did this stuff up here. Sorry about that. All right. That's the process then. So now, to sum it up, the first thing you're going to write is write the summation. A sub n is many delta x's times f at the starting point plus some number of delta x's over. And you know how to find delta x, yes? Yes? Okay. Then the next thing we did was we put in the function for that specific problem. Obviously the function will be different each problem. One time it's a parabola, one time it's a line. That changes it. Okay? After that, we separated into mini summations. That was the tedious stuff, a lot of algebra. Okay? After that, then we subbed in for the summations with formulas. Those are the 4 main formulas. Now, I'll pause here and say there's a huge limitation for this. This whole method is great and it works for infinitely many rectangles as long as there's a formula for what you see in the function. So there's a formula for, when you have linear, because we have a formula for to the first. There's a formula for area under a parabola because we have a formula for under a square. And there's a formula for when we have area under a cube. But there's no formula for area under e, or sine, or cosine. or square root, or a million other functions. So this is pretty much limited to just polynomials, and we're going to need something else for transcendental functions, and that's what calculus comes in, but we'll talk about that later. Right now then, after that, after you sub in for the formula, you take the infinite limit. The limit as n goes to infinity of your function using end behavior. All right, so now that we've done the whole process, let's do one together all the way through, and you have 1 on your notes and 4 on your homework, and by that, you'll start to be pretty solid and pretty quick, which is my hope. All right, so here we go. Find the area under 1 plus x cubed on 1 to 3. What's the first thing I should do? Okay, so then is the sum from 1 to n, we're using right rectangles always, of 2 over n. Delta x, or the width of each rectangle, is a region of 2 divided into n chunks times f at 1 plus 2 over n I. The x at which you draw the heights is constantly moving over, starting at 1 and going over at delta x each time. All right, now what do we do? Substitute in the function. 2 over n stays. In this case, the function is 1 plus blah cubed. And in that blah goes our x, 1 plus 2 over n. Cool?
Yes.
All right. Now I'm actually doing the worst case with you here. This is the worst case because distributing a cube out is gross. Remember, a plus b cubed, or binomial expansion, which actually is really useful in probability and statistics, so it's worth knowing, is a cubed plus 3a squared b plus 3ab squared plus b cubed. Again, now this is going to get gross, but again, this is as bad as it gets. That's what I'm showing you right now. All right? So, if I apply that here, then I think you'll agree that a would be the first term, and so in this case, a is 1, and b is the second term, 2 over n I. So when I say a cubed, that's the same as 1 cubed, or 1. The next one is 3a squared b. So I'm going to put that kind of basic blueprint down, and in place of the a goes 1, and in place of the b, 2n over I, or 2 over n times I. The next term is 3ab squared. In place of the a, again, is 1. In place of the b is 2 over n. And then b cubed is one big thing cubed, and that big thing cubed is 2 over n. All right. Let's talk constants, all right? Now, I don't know. I've done hundreds of these, literally. I've taught this forever. So if I'm going too fast or you don't know what I'm doing, then please let me know. But I am also going to try and boil this down to something fairly quick. The first thing we're going to have is a bunch of constants, all right? So my first summation might be 2 over n times the sum of a bunch of 2's. You track it? All right. The next thing I'd have is a bunch of I terms. Now what would be out front of that would be a 2 over n and a 6 over n. And inside the summation would be an I. And if you want to call that 12 over n squared instead, that's all the better. But whatever, it's fine to leave it like that. It'll be great. You with me? All right. The next term will represent I squared. So let's talk about what would be up front. We'll still have the 2 over n up front. And what other stuff will we be pulling up front? 4 over n squared and a 3. So altogether, 12 over n squared, or if you like, 3 times 4 over n squared, whichever, times the sum of a bunch of I squareds. Last but not least, we'll have a 2 over n. And what else will we be pulling out of that guy? 8 over n cubed, and it'll be times the sum of a bunch of I cubed, right? All right. Cool. Now we go to apply formulas. This would be 2 over n, and what is the sum of a bunch of 2's equal to? Or the sum of n 2's? 2n. This is 12 over n squared, and what's the sum of a bunch of constants from 1 to n? N times n plus 1 over 2. Feel free to, the back side of this has, or the front side has the notes, but I also will be happy to give them to you. The next is 24 over n cubed. The sum of a bunch of squares is on the front, but I can also tell you it's n times n plus 1 times 2n plus 1 all over 6. And then the last one is 16 over n to the 4th, and the formula for adding a bunch of cubes, 1 cube plus 2 cube plus, is rather strangely, to me, is like the square of the sum of the first two. That's calculus. Okay? Although it's third power, it's square of the, it's just great. Okay, that is a formula based on n rectangles. So what's the last thing I do? I take the number of, here's where you speak. I take the number of rectangles to, yes, good job, infinity, yes, thank you. So we're taking the number of rectangles to infinity. Now, I don't like to write anything, I'm lazy. So I just typically write, I've identified what a sub n is in my previous work, so I don't see a purpose of rewriting it in another step. I can do the end behavior just by looking right above. So what is the first term, simplified? So that's just straight up 4. That doesn't require any end behavior calculus knowledge. The next one is 12n squared over 2n squared. The n squareds wash away in end behavior, and so it amounts to 12 over 2 or 6, right? The next one, 24 times, let's see, the power-wise, it's n cubed over n cubed, yeah? All right, so n cubes will wash, and the numbers are 24 times 2. I can't tell you how much that 2 gets lost in the shuffle. 24 times 2 over 6 are all the numbers that will go into the end behavior.
Do we have to write that step down, or can we just go straight to the
What, this step?
Yeah.
Like straight to the answer? Like for
Yeah,
that part? Yeah, that's fine. Oh, 8. Yeah, you're right. 8. Yeah, I don't need to see that. Okay, and the last one. Is it n squared over n to the 4th, or is there a power match? Yeah, don't see that. Don't forget that square out there. It's n squared, n plus 1 squared. So yeah, it's n to the 4th over n to the 4th. And behavior does become about the numbers. 16 on bottom, on top. What's on bottom? 2? 4. Okay? Because that's square. So we get something like 4 plus 6 plus 8 plus 4. Or what? 18, 22. 22. All right. Try one all the way through. Actually, how's this going? I'm going to go by you. Do the one on the notes or do the 4 on the homework, or 4 on the homework. I don't want to waste your time, but I also want you to get good practice. Notes? Stop looking at me. Stop. I'll tell you what. Let's do the one off the notes. If you feel like, I'm going to do the one off the notes. If you feel like you can do it in your sleep off the, then go to the homework. And then, yeah. I'm glad you did that.
Really? Really? I don't believe that for a second.
Wait, you got those?
In terms of
The same.
getting to the answer, there's probably, see why you get my worry is that on multiple choice problems, it's often written with function notation. So I think that
No, never had it. Oh? I've never had to do that. Which one? Oh. This is. Oh, estimating area by rectangles? Oh,
just define it, not
are we allowed to jump?
sure we can use the summation and all that stuff. Maybe I'll do some fucking. Maybe I'll throw an extra credit on there, show you.
We can use this?
Well, that's a lot of
So we don't have to do it the whole thing.
You'll need to be able to do both, because not everything is equal subdivisions for one thing, so sometimes you're not gonna be able to do it.
I know how to do it the other way. Oh my goodness. Oh, which one's he do? Oh, okay, let's do number two.
That's.
Oh yeah, me too. It's not the last
Doing those notes, the answer you're looking for is 60 or 32/3. Okay. We'll do one off the homework just to see if you're doing that instead. How you doing? And we'll be good. Are you doing the first one on the homework or some other one on the homework, anybody?
Number 2.
You on the homework? Okay. Catch up to you and see how you're doing there. This homework, step 43, by the way, we do Monday because you have tests tomorrow. Test is tomorrow.
Instead of 4,000.
Just so your eyes are completely open, do you really need calculus to find the area under y equals 2x on 0 to 2? Could you easily do that geometrically?
You could easily do
I mean, what's the graph looks like this. So I know that's not a bad thing to know what your area is supposed to come out to. The answer better be 4. Okay. Right? Now, why do all this process? Because it's nice to practice on an easy one like this where you know the answer, so you can make sure your process on calculus is good. Switching gears.
Do we have, for the first step, do we have to have that first step where you put in F?
So that's a good question. That's the second time I've asked that. It feels like this step is unnecessary, and to go to straight here is fine. The reason I don't want to waste your time, don't get me wrong. The reason you might want to do this step is because often you'll get a multiple choice problem that is written like that, and you want to be able to recognize it. Yeah, that's why I want you to keep doing that. That one's actually, this one's really clean, yeah? Not a bunch of work, really easy algebra. Two was pretty easy. Try 3. I think it gets harder. 3 or 4 are harder. Actually, 26 you could do. All right. Get at least a couple down, and then I want to talk about the test a little bit, those notes section, but I'll let you finish that, and then we'll go over that.
Is it 2NI and 4? That's why. For what? Wait, are you going over this day?
Am I, who, me?
No, sorry.
Oh, okay. Sorry. I'll mind my own business. Oh, I should definitely.
Half of our classes.
Yeah.
No, there's 2 juniors.
Yeah, it's a substantial number.
Yeah. There's only 2 juniors. That girl had me.
Yeah.
She claimed to be Mom.
So 20.
What do you mean by class? I'm her sister.
Josh. Oh, yeah. Zane is here.
That's what you're in the sticker. A sticker you don't know. After that, I started getting this one.
Okay.
You're so chilling.
All right.
This is the live.
All right. How many months you doing? What'd you get for 3?
And I think the
8/3,
8/3.
I'm down. 3/3 I agree with.
Yes, Haley.
Haley is the champ. All right. That's it. That, yep.
For when you at the top you said A, should it be A? You have to put A in.
It should be a as a function of n, you're right, that's true. A as a function. Good point. Sorry about that, you're right, I cut corners, I tend to do that. Okay, whether you pay attention to this or not, but this is what I would focus on the test. When I make a test, I typically start with the cut, and to me, I write down, I look at the objectives on my notes, and I write the problems based on seeing if you met the objectives. First thing is, I think it says on the top it's through 42. That's not true. That's actually the what is it? Quotient rule. Right, that's the quotient rule which we talked about just yesterday. So that's due to. So it'll be through 41, and maybe a little 41, and maybe a little 43 fun sheet action. Okay. But not 42, the difference, the quotient rule is 2. All right. Rational functions, that's pretty clear. The idea on that was if there's a square, then there's no sign change. But after that, other than that, it's pretty much like we've been doing it before. Top, you look for holes, top zeros are x-intercepts, bottom zeros are vertical asymptotes, All right, you with me? Normal line. Step 40 actually had 2 topics. Step 40, normal line is like tangent line, except the slope is opposite reciprocal. Opposite reciprocal. I can tell you the thing I would warn you about that is notation. I looking at some of your homework, I would just absolutely rip you for notation. Some of you will. I will give you an example here. If you had y equals sine of x, and I wanted the normal at whatever, pi over 6. Okay? What's the first thing you do? Find a point. Okay, so pi over 6 and sine of pi over 6. So what's the point on the tangent in normal line and the curve itself? Pi over 6 and sine of pi over 6 is 1/2. Okay, cool. Then you go about the slope process. Here's where your notation needs to be good. How do you find the slope? First take the derivative, okay? You need a notation for that. If you just had a floating cosine, that stinks, okay? The derivative is cosine. Preferably then saying at pi over 6. What is cosine at pi over 6? Root 3 over 2. Here's where the atrocious notation tends to come. Then people say, okay, now I need the normal slope. And I actually have people write this, okay? Wow, I can't even begin to tell you how much that makes me sick to my stomach. You just said those are equal. Are you kidding me? Those are equal? Those are not equal. That's terrible, terrible, atrocious math. Shame on you. Okay? More like the perpendicular slope is -2 over root 3. And therefore, y minus 1/2 is equal to -2 over root 3, x minus pi over 6. I would have a point built in for finds this tangent slope. If it's not labeled by the derivative, it's invisible to me. I don't see it. Okay? I would have a point built in for finds the normal slope. If it's not labeled, it's invisible. No point for you. Okay? You must label. Interpreting the derivative, gosh, this goes to the basic format is something like this. F prime at x, or whatever, usually these are word problems, so you're not usually dealing with F prime, you're dealing with the change in number of people, or whatever it is, okay? It's usually a function of time. Is the rate at which blank is changing at time equal blank. And if you're dealing with a specific case, if you're dealing with a numeric case, in other words, if I told you to find the derivative at 2, then you're going to have a number, not just a general idea. And when you go to interpret that, you not just interpret that as change, but how it's changing, increasing or decreasing. So if you're dealing with a number, a numerical derivative, interpret the sign, which is to say increasing or decreasing. I would strongly recommend you look at your notes. Look at the notes for that set, because there's a ton of examples here. In fact, I might just fold it. All right. Estimating the area by rectangles. That we've done a lot, and so hopefully you're starting to get good at that. You need to be able to do 5 different methods: left, right, upper, which is the same as circumscribed, lower, or midpoint. If you're not familiar with that vocabulary, you need to study that vocabulary. Circumscribed is the same as upper. Inscribed is the same as lower. Don't come up to me during the test and say, does that mean lower? I'm going to say, get out of my face. Upper is circumscribed. Lower is inscribed. I encourage you to make sure you show clearly the work. I expect something like this: F, 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 cha, cha, cha. That to me is more important than the numbers. This step is what I grade for. Shows me at which point you found the height. I don't want to have to look at a 4 there and figure out where did it get 4 from. That's not on me. That's on you. Okay? So you need to communicate that part. That's important to me. Second, and I'm talking even to Cal Honors students, if you look back on your set 39 extra practice or something like this, many of you just, anytime you do these, you automatically write out. And even if I told you that the function is named G or H, on the AP test, you absolutely response to that. You must use the function name given. If they call it H, and it's H at each list. If they call it G, then it's G. Don't just assume everything is F. It's not. All right? So use the function name given, not just assume it's just general. Yes, we will call that not being in the problem. All right. Equal subdivisions you've done a ton of. Unequal, we probably need to practice that a little. There's one in the practice. It's a tangent problem. Square root is a good problem also. But you might want to look at your notes for that. There's not much practice in the book. Over or under estimate. Do you know how to justify whether an area estimate is over or under? Give me a justification statement, please. Actually, here's a curve, y equals x squared. And you're using left-hand rectangles. It would be an underestimate. Okay, now, underestimate would be one point. Saying y would be the other point. Y would not be because the rectangles are below the curve. That doesn't cut it. It has to be because I'm using left-hand rectangles on an, and that's 2 pieces of evidence. Not it's an increasing function, or not because it's just left-hand. I'm talking into your 7th hour. I'm sorry. I should.
It's fine.
You
It's fine.
stay here. You can like walk around. I know I'm a teacher. I'm supposed to know that, right? Is there anybody in the hall? Well, it would be over. Let me finish, okay? Then you can chill. Okay, do you mind?
Mr. Mann,
Yes.
do we have lunch all at the same time?
Same lunch. It's just after this kind of added 7th hour. Okay. So the whole schedule is good. Interpreting area under a curve. I beg you, please just look at the units and think Unit multipliers. Hey, I'm still under area under the curve. If I tell you not just, hey, this is some meaningless function f of x, but I tell you this is a function that tells me how many your rate in problems per minute at different times, and say your rate is really slow at the start of the problem set because those are word problems, and really quick or greater rate after. When you find the area under this curve, it's not just some random meaningless experiment anymore, it has meaning. You're talking, when you find that area, you're taking problems per minute times minutes, and you're finding problems. The area would represent problems done on some time. Okay. That is one of the greatest applications of calculus, is accumulating the result of a varying rate. Integral of the sum, 1 over x, for the most part those are going okay. Do you know your power rule back and forth? Okay, good. Differentiability, this I hope you have more room to work than I do, because I should have given more space. Differentiability, there are 3 reasons a derivative doesn't exist. What are they? Sharp turn. What? Discontinuity. And vertical asymptote? No, that's a discontinuity. Vertical tangent. Vertical tangent means that the derivative is rise over run, and if it's vertical, it's rising but not running. There's a 0 in the denominator. That's why the derivative doesn't exist there, because it involves a 0 in the denominator. All right? Would you write yourself one more note and then I'll shut up? This plus implicit differentiation. You have a horizontal tangent if dy dx has a 0 in the top. You have a vertical tangent if dy dx has a 0 in the bottom. Common AP question is to find an implicit derivative. Basically like that derivative problem, that AP problem we did last Friday in class. Remember that? Yes. Maybe you killed it. That'll be a good preparation if you look over that. Or if you want another one, I can make you one. That'll be good. All right, and then the rest is just odds and ends, big ideas of calculus. Every test will have a combination of these skills: product rule, quotient rule, chain rule, product rule, chain rule, all the different derivative techniques. Plus, do you know what to do with derivative? Can you find a horizontal tangent? Can you find where a function is increased? Can you find a max? All those are applications of the derivative that you need to be able to put those two together. You with me? All right. If you need to go to the restroom, one or two at a time, that's fine, but I don't think you're supposed to be out walking in the halls too much. So I'm sorry to take you into your homework time. I'll shut up now, and you're here till some time. I can't remember what.
Do you have a pair of scissors?
I do.
Can I have them pretty soon?
I'll put up the schedule once I find it. Just a second. Hey, how are you, Alan?
Yeah, that's actually.
Oh, I'm sorry you're not doing great.
Yeah, no, it's just one question that I was asking. Oh, also, can I take the
Quiz?
quiz tomorrow, third hour? Or actually,
Sure, that's fine. They're taking a test in here anyway, so all the better in the hall or in here will be quiet. Okay?
great. And so the question is, what is the total differential? As in, like, what are you finding the total?
When you find a total differential,
Like, I know the basics of it.
I would have to review it and
Oh,
get back to you tomorrow, because I don't.
I can give you the formula.
Okay, sure.
So it's just for
That's
a z equals y graph.
Okay.
Delta z equals partial derivative in the x direction plus partial derivative. You literally don't know why. What's dz?
So it would be a tiny amount of change in z, which obviously that's surface, but what is it? So let's say, and I might be going to look at this, I'll just, we'll think it through together, and maybe it won't be really good. Let's say z is.
Well, oh, wait, I forget, that's like where the actual graph of the
So I'm visual, so I gotta do it. So when I
like zeros, all we learn is how to graph it by setting each other.
So the, oh, the traces. Oh, yeah, so you grab by the traces. That's cool. So when we
It was like principal pages.
I got you. All right, so let's go back here. Maybe this would help to go back and do the differential idea of two dimensions. When you do, say, you do white graphs, and you typically take the derivative, and then set it up. Right now, in two dimensions, and this is saying that the change in y corresponds to two things. First of all, you would have to talk about the rate of change, or the rate at which y changes with x. In this case, this derivative is really saying that y would change twice as much as the x at any point. So, for example, when x is 1, if I were to change, at that point, if I were to change x by 1, y would change 2. If x were 2, then I would expect y to change 4. So it's a comparison. I like to think of this as a fraction of how much y would change for any change in x over 4. Well, you don't always want to change x by 1. Sometimes you might want to say, oh, well, if I only went over to a half, how much would y change? Well, that would mean then that you want to take the rate at which it's changing, which is 2 to 1, and only times an x change of a half. That would mean y would only change by 1 unit. So this is here to say more like, all right, yeah, this is the generic rate of change, but times an amount of change in x.
Like the minuscule amount to be a minuscule amount of y.
Exactly. Based on how much you want to change x by, that would determine how much you want to change y by. So the rate at which, the relationship between how they change against each other times an amount of change in x gives you a amount of change. So 2 dimensions, or 3 dimensions.
So then if you change x to y by a minuscule amount, that's what will be a total change in z.
Exactly. So this is like saying how much will x, or how much will z change with the little changes in x, times, and that's a rate of change, times however much you want to change x by, and then you're going to add how z changes as y changes, because obviously in 3 dimensions, if you got a curve like this, if x changes a little, it will change z, but also if y changes, it will change z. So you actually have to accumulate change due to both things varying, and that's really change, result of change. So I would think of this as change in z resulting from x changing, and then add to that the changes in z resulting from y changing, or from y changing.
Yeah, that helps a lot.
Cool, thank you.
Yeah.
All right, so you're gonna take the third hour tomorrow.
Yeah.
Do you have any idea if Peyton's is still even in this town? She didn't already took the old.
Yeah, well, the thing is, she actually like passed out. Oh, it's not Friday.
Oh,
Thursday. She's got one of the Yeah, so she has a lot of it back.
I assume she's
Yeah, or actually, that's sort of giving up this last little bit. I'm trying to keep up with motivation, but she just doesn't like that last thing.
so maybe I should
I'll talk to her about it too.
All right, I appreciate you.
Thank you.
Yeah, guys know she only had two.
What are you doing? Okay, go ahead. So, I would say, I don't know if you've heard of something.
Yeah.
All this part-time.
It's like they're just
That said, like giving the answers, so the whole problem is really not just coming out of the answer, they're giving you very clear areas for
baseball is a story.
All right, so A's Jordan, A's Jordan. How is he? You're good? Okay. Yeah, it's fine. So that was- Says we're starting to get a little harder. So does this make sense to you, or is this your work, or is this from? Yeah, so you definitely show you this would be the first zero, and then understanding writing top zero bottom zero.
Probably is your story.
So zero to the top has to be fine. If they ask for the verticals, then you would be saying 2 minus x. In this case, now a lot of people didn't stop this because they're showing them the points. It feels like, well, that's where you often unpack not just with one number, like derivative, but also the original number of those. So you take this to, if you put 1 0, try to do that. But this curve, somewhere over here, it exists. Cool. You got it? So D would be a problem where you they're kind of like illustrating. There's hidden points in there that are easy to do. Some you're just kind of struggling with. So the first thing I would hope that when you get through this is when it says the function of time, you're going to consider not how they change with respect to each other. Usually we say dy change as x change. Sometimes they just total underline that doesn't even show up in the equation. And that's when I read this, dy dt or minus dt, that means instead of doing the derivative like we did first here, it's not taking the derivative with respect to x. It's taking the derivative with respect to y. When I say chain rule, you take the derivative with respect to y, that means it's kind of using derivative like you're like there, but then take the derivative of the variable itself, because the variable is being eaten. So that's where this is coming from. 2y
Like, you know, like I played this game, and then you just
then
say,
times the derivative.
days,
2 is
it's not a ton.
doesn't pass with respect to and then this was probably with respect to times. When I say first setting, that's complex. But then you're going to multiply that by the derivative on the set. So that should be dy. That should be
I have no idea.
All right, so the
field for it, says a planet with 5, in this problem,
No, it's not.
You know what she looks like?
which would be the number.
I don't know.
Now, it's up to you, because some people learn science to
Find the critical
solve the equation of variables and then put in the numbers. Some people do it more what I
I don't know how to do it, so.
Lyrics, and then
Oh,
solve.
wait, actually, it's
Find the domain.
Yeah.
In this case, then we're,
Domain.
I solve that with T.
What is that? How do you find the domain?
C, so I would just do this, like, so. This guy.
You have to set it.
After that, then it's numbers, so this, it feels like a very own three, but there actually is a little more. The twos from obviously, why they give you, so that's what you do. And do I see they give you, that's what. The only thing they don't give you is that.
Why? Why do you do these things? I don't know. I don't want to hold it.
Find the domain.
She's not.
Because you can't have a perfect.
You know
What?
an X, you want to go
What is
back
the
to
domain?
X, a region.
How do you find the domain?
This is your equation. And if you know y is 3, you can plug y at 3 and say, oh, when y is 3.
You can't do that.
What this, oh,
Because you can't have greater
so
than.
you need,
It's
you know,
Not negative 2 be equal to negative 2. I should have taken my chance.
Well, I got it.
What do you do with it? Oh, yeah. She's a self-love. Does it? Yeah.
It has to be less than negative 2, right? No, it's not negative 2.
It can't be negative 2. There can't be negative 2.
Yeah.
I will, so I don't know what those are.
You're not gonna let us go.
That's so cute. I hear you. It is now.
What? Can I trust your drink?
That might be the best one.
No, actually, so you know, what I would want is
These are bro conversations.
What? So what is the domain?
The domain, I think, is less than or equal to negative 2. It can't be negative 2. How?
Because if you plug in negative 2, then it's equal to negative.
No, it's squared.
Oh. Oh, now I feel dumb.
anyway,
That's all it is.
That's why I didn't know how to do it.
It'll ask you.
He said that to you?
that right?
That's the minimum maximum. If something's increasing, you want to know if that's greater than that function is increasing.
And you find a derivative?
No.
And she's
Find a derivative. So it's like
Yeah.
what?
So now we need to,
They haven't?
we need to assign start and stop being positive negative on zero. So now you need to assign a zero sum.
Wait, let's do like this. Basically, yes, it's
Assign zero
like one.
and two x.
This is the change. That was embarrassing. Tried to be so slow. They're the worst way.
Sign is zero.
These ones are
Sign is like what?
No, there's just
we don't like them.
but I want to try it.
No, I told you it's a weird flavor.
The texture is weird.
You don't like anything?
Oh,
It's so
Why'd you-
that texture. How do you get stuck in your teeth like a mom? Yeah, okay, that's
sorry, you were right. I was thinking like, not about the drink, I was using the wrong font. So you're right. Coast is zero. Curse is. And I might need more. So now that's what 2x would be, which would be x would be 4
do this.
divided by 4. Now, because I just divided by 2, I'm still a pretty small number, so I'm nowhere close to the top of this.
I don't know though, Amber's mad.
Any comments?
What?
So after 2
It's okay. There's lots of
Okay.
things.
Honestly,
You guys are only so much I can do. You guys.
we go up here and this either had two. So if I went the first time, I would be going that way. Just keep going, that would be 3. So that way, if we had gone past the 2 files, we'll get to and then one more time, probably number 5. I was going to say, one way to one sentence.
Oh, yes, there's cross pot. Next. Not this Saturday. Next Saturday. 16. Okay. If I say, if it's Monday,
I would be able to tell you.
yeah. No, but if I say next Saturday, you could be like, oh, so this Saturday. Yeah. It's something else. I don't like this. I don't know.
Let's go
I'm
with
scared though.
industry hybrid.
Just my house or something. I mean, it is. You think it's not small. But it
Yes, sir.
Are they just really small?
Exactly. Like, yeah, exactly.
Can I see how you do this one? No, no. I don't know what to say. Sure. If I make it the domain as plus is greater than equal to that, is this right?
Square root of 2 screws everything up. So I would, rather than do it very by the book analytically, I would think more conceptually or kind of just think. Now, I totally agree with you looking at 2 and negative 2. But in terms of where the squares greater than or equal to 4 would be, the positive side is pretty obvious. Yes, anything above 2 would work. But it wouldn't be x greater than 2 or negative 2 because greater than negative 2 would equal to 0. What has to on the negative side, in order for the square to be positive, to be greater than 4, it would have to be that.
Yeah.
So it should be more like x is. So when you do this, it's one of 2 ways. You either say it has a disjunction, x is greater than or equal to 2, or x is less than or equal to negative 2. You will often see the absolute value of x has to be greater than or equal to 2. And that is another way of saying it has to be on the outside.
Okay, and so for this one, would this one be correct?
Yes. Yeah, that's a conjunction because you want small x's. That one's a disjunction, you want large x's. Exactly. If this had been x squared minus 4,
Then
then,
it would be like that.
yeah, exactly, you would need big x's to overcome negative. Whereas in this case, the term, you want small x's.
Run them on. Oh, damn. You and Chad. It's like 36. I didn't make you feel.
Watching a funny video. You don't watch funny videos in the classes when he's about to take the test. What's going to be on my mind? I'm just going to put a whole class. Nail that, right? And everybody else gets kind of on for that because everyone's doing the same test. So when today, everybody leaves speaking because the test was on.
Rats.
You got him a 10. Which one did they want you on 10? Great French pastry.
Who erased the little things that on it?
Mr. Rickman, did you erase the board that the little fella that
Say it's Phil's birthday.
I did not, but they erased me. There was a little Bella on the board, but there was a little
little
girl.
fella was in his class? It was in his class. So he was
Like this period?
Yeah.
Oh, Alan and I were working on a problem, he probably erased it. Sorry, feel free to put it back. Sorry. It's not profane, is it?
What?
It's not, it's appropriate, it's not.
No, yeah, it's
Okay.
funny. It looks like that guy, but with
Can't say it from your, oh, okay. Okay.
Okay, if you do the line, so then I don't, I'm asking to do it something.
that one's better.
I feel awkward.
Is that a mustache or a nose?
That's like a little chin.
That's a chin?
In mine.
Like a little-
We drew the other one. I just
It's literally the face.
Oh, I know they did.
Hi.
So fun.
Yes, which one? So that's a good question. So the first thing you should look for is if there's a hole. If there's a common factor, it's all about is there a common factor. If there is, then find the hole and then for the rest of the problem just study it out. In this case, there is not a lot, so so then what would you do after? That's correct, that's no easy zero if you're figuring.
Did you finish
That's
this
all.
one? Yeah.
Okay, so you're there, so that's your favorite one.
Who knows, man?
So this guy, yeah, now. These two,
Why is it
they're
on
both
stereo?
twos up to see what they really mean. When you have an exponent, double on a vertical asymptote, it'll be more the case that it's a vertical asymptote and there's no sign change. No sign change, that means it's either below the axis before, or above the axis before. So don't think down so much as no sign change. If you see a square, meaning no sign change. On an asymptote, that means on an intercept, the next intercept is no sign change and such a point has a so no sign change. For that
Hurry up and don't be late.
the only thing that, yes, the only thing that really does for you is it does determine memory. This is there or not being there. It's definitely the difference between the 44 horizontal asymptote because the scholars are equal, or the exact scholars are so much more denominator. And so in this case, when I look at the end, overall, this is x cubed on top, and a bunch of other little stuff on the bottom. It's like x cubed, overall, the bottom is much which probably goes faster, this will approach zero. So that'll come indicate here, and that did go into that indicator that. So it's, that's same helps you. Good, excellent. And then the top is extension, right?
Thank you.
You're welcome. Oh, oh, it will, okay. Yeah, that's nice.
Oh my gosh, is that doing the wrong offset the whole time?
So, so you might be.
No. Oh my god, did that work? Oh my god, it worked. It worked. Yeah. Oh.
Are you saying that it
No, it may worse than it was, right? We don't want that platform.
Who's that?
Don't put it in my
I don't know.
It's just me down, slicing it. Oh, like I was just sort of down.
Where did it go?
What is this?
That's epic.
Is that a foul?
Like,
It's so high. Why would you ever get that? I'll let you talk for the guys. Yeah, you are. You're forgetting that. You always get the nose.
No.
No, you're.
I have no idea. I'm gonna turn this in. Do you want me to actually?
Whatever you do.
Well.
I think I get
Yeah,
it.
it's in
These are fine.
That's my phone screen. Almost 123.
Oh, look at her.
That is yours.
I did it all.
Baseball. I know this one. I like from Jackson City.
Oh, this is high, and this is high.
Okay, that is how it is.
What is your conversation with Guys, let's sing on the door.
All right.
Really?
America's.
What?
Okay, bye. Have a lovely day. Or the lunch on 4th, depending on your normal schedule.
I'm just sitting here with pencils on.
I've got quite a
Maybe you can have the cracker, I'll have the salt.
That 42 got grade, if you don't, I'll take it.
Okay, well, there goes my life. Let's just take a trip to the ER.
I'll take it Monday.
Anderson.
Why is he broke?
Let's go to choir.
Some picking those up from you or I'm sure you would do it for you.
I would.
Thanks, gentlemen, like that. Even though his underwear's hanging out.
Even though what?
Have a lovely day. Depends on you. Oh, shucks.